on
Sure.
your screen.
Yeah. Let me try to do that.
They will come. They came here. Yeah, they came here and went back. Yeah, they thought it starts at 2 o'clock, so they came and back. Maybe they will come back. Yeah, they will come. Yeah.
Wait a
Should we
second.
wait?
Hold on.
Maybe we will wait 2-3 minutes so that some
Sure,
of the
sure.
people will come.
Absolutely. Yeah. You want me to stop sharing or?
No, that's fine.
Okay. Yeah, I'm sorry I could not be there in person. It was just a bit too quick.
That's fine. That's fine. Check. They're coming. Yeah. Okay, we will start. So we are happy to have Svendu. He'll be talking about a dictionary to test GR with gravitational waves from observation to theory. Svendu, you can start.
All right. Thank you again for giving me this opportunity to talk to you guys. I apologize once again for not being able to be there. It was a lot of fun when I was there 6-7 weeks ago, so I really wished I could be, but yes, sorry that I couldn't. Um, right. So today I'm going to tell you about something that I've been very excited about. We finished working on this 3 months ago. Before I talk specifically about this, let me give you a brief overview of the kind of things I think about. So the main goal of my research has been to understand the fundamental nature of gravity from all aspects. I've worked on every aspect of, or many aspects of this problem. So I worked on the more mathematical and formal part of this, working in higher dimensional QFTs, etc. And then I have also spent a lot of time working on the part which pertains to observations and things which are relevant today. That has been the main focus of my research in the last few years. So the two main things that I've been thinking about in the last say 3 years are objects. So essentially testing the nature of gravity, which I put here, and then testing the nature of compact objects, which I put there. So when I was there in September, I talked about the nature of compact objects. So today I will talk about the other side of the story, which is testing the nature of gravity. So the idea essentially is because I would like to know what is the fundamental nature of gravity and how do you test it. So there are two avenues in which things can differ. One of them could be that the objects that we think are black holes are maybe they are not black holes and they're different compact objects. And how do you test for this? So this is something that I talked at length last time. So I will be very brief about this. The other side, which I did not talk about last time, but then there were some questions which were alluding to this, is if you still consider black holes, but you consider modifications to gravity, how do you test for that, and what are the implications, and how do you systematically do things? So this is a very exciting avenue, which I'm going to describe to you about. Okay, so before going to beyond general relativity and talking about modifications, let's celebrate GR for a second. So this is the most, or one of the most famous predictions of GR, which kind of led people to believe that GR is correct, which was the GR predicting Mercury's perihelion precision. This was in very, very early days of GR. Then one of the biggest milestones, which really convinced people that GR is not just a mathematical curiosity and a weird way of writing things, is when Eddington got his famous solar eclipse plate. So this here is a picture of the original plate. I was fortunate to see the original a few months ago in the US. So here is a picture. So it's actually funny when this was shown in a press conference, and then Albert Einstein was there, and people asked him what would be a reaction if the solar eclipse predicted, or if your prediction of the solar eclipse turned out to be wrong. And Einstein said, I would feel sorry for the good Lord. The theory is correct. So he was absolutely convinced that GR is correct and nothing could go wrong. And all of this was just confirmation for him. Okay, good for us that this is exactly how it is. And then we can go back, so we can go forward to the 70s, where the famous Hulse-Taylor binary pulsar was discovered, which confirmed that the power loss for a binary pulsar follows exactly what GR predicts, and this was awarded a Nobel Prize in the 90s. So all of these things are confirmations of GR to very high accuracy, which is to say that GR is a very, very good theory, and there's no reason to just throw it away and think about something else. But all of these are weak field tests in the sense that you're either doing things at the solar system scale, or you have very small masses which are very far away. So the curvature scales involved are very small and weak. However, now we live in this golden era of gravitational wave astronomy, where we can do strong field tests, where we no longer just have to rely on gravitation, or on curvatures being weak and things being far away and small. We can actually talk about observations where things which we think are black holes are very heavy and compact are merging. And then if we are smart enough to understand what is going on and predict things, then we can actually access strong gravity. And even in this regime, which was, so again, this is the 10th year of the first waveform, this is 150914. So these measurements confirm what GR was telling us. So GR is still highly accurate, and there is absolutely no reason to think beyond GR if you just go by these observations. However, as you will see, there are error bars, obviously, in these experiments. So we have tested GR to very high accuracy, but the kind of modifications we expect should supersede what GR is. Those should happen at high enough energies, the kind of energies which we still don't have access to. So then, given the success of GR in all of these strong and weak field regimes, the natural question is, why would you even want to go beyond GR? And for me, really, the answer is twofold. Firstly, black holes are singular objects deep inside them, and this somehow makes me uncomfortable. So I would personally think that if I go close to a singularity and my GR solution breaks down, I would like to know what supersedes it and what fixes it. And usually the words that people throw around it are quantum gravity is going to fix it, which just means that you're going to get some other theory of gravity, which is going to take over once you get close to very, very small distances. This is usually what is meant. But since we don't have such a theory fully formed that is applicable to our universe, the question is, how do you make progress in this direction without knowing what this theory is, or without having all the information? In this context, one way to make progress is by thinking of corrections beyond GR as an effective field theory, where you say, okay, I have my Einstein-Hilbert term, but then on top of it, I can write down extra things. And if I write this down in a sane way, where I have some control on my effective field theory way of doing things, then maybe I would have some idea of what is going on. So this is an approach that people have taken for the last 30-ish years. And now with the advent of gravitational wave astronomy, things have gotten into high gear, and people have actually started making real progress on how would you figure out what these corrections are, how would you go around testing them, how do you predict them more accurately, and so on. So this is kind of the context in which I'll be talking about. So let me kind of characterize what these beyond GR corrections are. So this is my cartoon way of representing the things that are most interesting. So here on the right-hand side, you have the higher order curvature term. So if you think in terms of adding higher curvature terms, so instead of just having the Ricci, you could have a function of the Ricci. You could have derivatives of the Ricci. You could have Riemanns, and you can involve multiple Riemanns. You can have three of them contracted in different way. You can have P of them. You can go crazy. You can keep doing what you want here. So this class I would call higher curvature terms, which only involve curvature tensors and their contractions in whichever way you want. Okay, on the other side, you can have something where you have new field content, as in you can have scalars coupled to the curvature, scalar couples to combinations, functions of scalars coupled to any of these things. You can have vectors. You can do a lot of things. All of these is again in the spirit of EFTs, where you're preserving the symmetries that you want your theory to have. If you want to break those symmetries, if you want to do Lorentz violating things, people have done many different things. There are Einstein ether theories or Java Lifshitz. So these are things I will not consider. I'm just listing them here for the sake of completeness. You can also do non-local things again. So things on the left-hand side, I will not consider. I will only talk about things on the right-hand side. So there are possibilities where you can say, okay, can I look at non-local interactions? And then you will get terms like this. You can also say, okay, can I go beyond 4 dimensions and look at higher dimensions? So depending on your motivation, you can write down things like that. But then the point of showing this is there are many, many different ways of writing down things which go beyond GR, all of which have different motivations. But from an EFT point of view, I will restrict myself to this right-hand side, where I will talk about higher order curvature terms and new field content and combinations of this. And this, for our purposes, will be a very agnostic way of not committing to what kind of theory things come from, but to actually make progress starting from Einstein Hilbert, you can keep going up, and then you can start seeing what is going on. Okay. So before we actually address what modifications are, I think it's useful to understand how does one test for any kind of modification to GR in the context of today's observations. So the tests that are done today can be broadly characterized on the spectrum of being completely model agnostic, which is on the left, to being completely model specific, which is on the right. So the model agnostic tests, which make up most of the tests that are done in the testing GR group in the LIGO Virgo Kagra collaboration, essentially what they do is you make as accurate predictions from GR for merge. So if you have a binary black hole system and they're merging, or a binary neutron star, you take them, you compute as accurately as you can what the waveform should look like, and then you compare it to a real waveform that you see in your detector. And then you try to see how much is the mismatch. And to characterize that mismatch, you can put different knobs, which tell you essentially at which order in post-Newton. So I'll explain what a post-Newtonian correction is. But essentially, there are parameters which you can choose. So there are different knobs you can tune. And then the aim is to characterize the deviation from the standard GR waveform, which you have computed to as high accuracy as you want, and to see how does it differ. So then there are different ways of parametrizing it. Some of those are called parameterized post-Newtonian. You can have parameterized post-Einsteinian. There are consistency tests between the inspiral and the merger ring down, etc. So all of these tests are very good ways of capturing if there is a deviation from GR. The problem is, if you see a deviation, you have no idea what kind of theory causes such a deviation. You wouldn't know if it's a higher curvature correction or if there was a scalar field involved. So these are good for detecting, but not good for telling you where it came from. On the opposite side of the spectrum, you have model-specific tests where you kind of do the opposite. You start with your favorite theory, let's say Einstein's scalar Gauss-Bonnet, or Riemann to the P, or quadratic gravity, or cubic gravity, or dynamical. So you pick your favorite theory. You try to solve Einstein's equations non-linearly, try to do a binary merger, and you compute the waveform that comes out of it. And once you have the exact waveform, you compare that to LIGO data. So you see, this way of doing it is not going to capture everything. So the way you compare things to data is by doing something called matched filtering, where you have what you expect, you get the data, and then you slide the data across what you expect to see. And then if there's a match, you get a big peak and you see, okay, I have seen what I wanted to see. So in this approach, you can only test for the theory that you have picked. So you can spend a lot of effort picking your favorite theory and then doing it. But because the theory space is infinitely large, it's kind of a losing battle to do this for every possible theory. Also, not every theory allows for a well-posed formulation of the equations that you want to solve, so you wouldn't even be able to compute waveforms exactly. So given that this is the current state of the art of how things are done, the question that we asked ourselves is, can we do better? So essentially, is there a way where, driven by observations, driven by the data that you see from the merger, can we construct a dictionary which will take us to a class of theories that it came from? So it doesn't have to be the specific theory. So it's not like model specific, and it's not completely model agnostic, but it sits somewhere in between. So this is exactly the work that I'm going to talk about today. So this was done in collaboration with these 3 collaborators. This is Laura Bernard. She's a faculty in Paris. This is Luis Flener. He's a faculty at Perimeter Institute. And this is Ricardo Sturani, who is a faculty in ICTP Sao Paulo. So this paper is now this is now published in PRD and has been the editor's suggestion. So the idea. So let me formally give you a toy model of the question that we're trying to ask. So imagine that you start with Einstein-Hilbert, which is this, and now you add some higher curvature correction to it. So here I've written this as Riemann to the P, meaning you have P Riemanns contracted in whichever way you want. And then because each Riemann has two derivatives of the metric, so if you have p of them, then you have 2 times p derivatives of the metric. The Ricci has two derivatives, so then you are left with a power mismatch of length to the 2p minus 2. I'm working gravitational units where g equals c equals 1, so then length is equal to mass. And then this is why I have this extra mass power, which is capturing my dimensions, and then I have some dimensionless coupling here, alpha bar. So the question is, if I start with such a theory, and I go all the way and I compute a binary merger in this theory, how is the waveform going to look different? So if you do this enough times, you will realize that the waveform is going to look different in two ways. It's going to be the standard one that you expect from GR, times something which scales as the velocity of the orbital velocity of the binary, and then something which scales as this new mass scale, which is the scale of new physics, if you will, divided by the mass of the binary. And then they're going to have some characteristics powers. So the question is, so the right hand side is what you see in an observation. So if I observe that I have deviation from my GR waveform, which goes as velocity to some power A and then mass to some power B, can I write down a dictionary which will tell me, given A and B, what is P? Right. So this is the question that we are trying to ask. And it's not just for things which are Riemann to the P, but like I showed you, you could have derivatives of Riemann, like derivative to the N, Riemann to the P to the N. You can have scalars, function combinations of scalars, etc. So the question was, can you do this for every possible class of theory that you can write down on the left side and then construct what is going to be the right hand side? So this is what we have done in this work. The upshot is, so this is like the one line summary of the whole work. So what this analysis tells us is that if you see something in data which goes as at least so where the correction starts at 5 post-Newtonian order, which means that this coefficient A is at least 5. Yes.
Suvendu, sorry, can I interrupt for just 1 second?
Yes, please. Yeah.
So just wondering, so higher powers P, they are suppressed compared to a lower power, or what? And what is the suppression that you get?
So the mass scale here, m lambda, is so this is the scale of new physics, right? So this is some mass scale. So the higher the P, so the bigger P you have, the more powers of m you're going to have here.
And what is the scale downstairs for it to be a suppression?
Okay, so this is right. So this is in gravitational units where length is equal to mass, right?
Okay.
So this is a small scale. So in contrast to high energy units where you would have seen a 1 over length here, or a 1 over mass here, and then that mass would have been large.
So that capital lambda is m Planck, is it, or what? No.
So it depends on what you want to pick it. So
if I introduce m Planck, is it that higher powers are suppressed by m Planck, or is that not true? I don't see m Planck here, so I don't know quite how to map and.
Right. So okay. So if you want to think of m lambda as m Planck, then sure, the higher you go, the more powers of m Planck you're going to have.
But it is in the numerator. I want things to be suppressed.
Yeah. So right.
So I'm all confused on how higher powers are. I'm just not able to see that.
Yeah. So right. So the difference is because we are working with high energy unit versus gravitational unit. So if I wrote this in high energy units, I would have a 1 over m Planck to the 2p minus 2. Okay. So in high energy units, you have h bar equals c equals 1, which means length and mass go as inverse of each other, right? And that's the role of h bar. If you take g equals c equals 1, then mass goes as length. They scale with the same. They scale the same way.
Okay.
Yeah.
All right.
Yeah. So it's just a matter of units.
So in high energy units, you will get 1 over m Planck to the
1 over
2p
absolutely.
minus 2.
Yes.
Okay. All right.
Absolutely. It's just this thing goes to the denominator instead of numerator.
Yes. Okay. Thank you.
All right. Thanks. Yes. So the upshot of the work is the following. If the deviations that you see on the right hand side start at 5 pn, then what it tells you is that the theory that it comes from can only have higher curvature terms, and it cannot have scalars or higher derivatives. However, if the deviations that you see in data are below 5 pn, then the theory has to involve scalars or derivatives of scalars or curvatures or extra degrees of freedom. Right. And then in addition, if you look at how does the whole thing scale with the mass of the system, so if you put this information in, then instead of just saying higher curvature or scalars or derivatives, you can actually narrow down and say what this power of P should be, or how many derivatives you have and how many scalars you have, right? So you see the power of the dictionary. So the way you construct the dictionary is by going from left to right. Of course, you take your classes of theory and you do it. But once the dictionary is constructed, as I will show you in a few minutes, the way to read it is from right to left. As in, you look at data, you see at what PN order do you start seeing corrections from GR. and how do they scale with mass. So given these two numbers, A and B, this is sufficient to already narrow down what kind of theories what kind of theories are responsible for these kind of deviations. So the advantage of building a dictionary like this and then taking this approach is that once you know, let's
Just
say
one
that
question.
nature.
Yeah.
Sorry. Yes.
Some of the higher curvatures can be written as scalars plus derivatives as well, using some Lagrange multipliers. So how do you distinguish these two really?
Right. So in general, if you have any higher curvature term, this would okay. So let's say you start with some higher curvature term and you write down the equations of motion for the spin 2 particle. You can actually decompose it into a massless spin 2 particle, which will be the usual graviton. You'll have a massive spin 2 mode and a massive scalar. So in general, you're going to have 6 degrees of freedom instead of 2. So 2 from the massless scalar, 1 from the massive scalar, and then 3 from the massive graviton. However, because you're making observations at stripe plus, which is asymptotic infinity, all these massive modes are going to die off. So the only observations that you're actually going to make in the context of gravitational waves are the ones where you have a massless mode which is propagating. So the only real massless propagations that you will see are going to come from either higher derivatives, or if you have scalars in the game which are actually showing up in terms of scalar radiation or gravitons coupled to the scalar. So if you have these higher curvature degrees of freedom which masquerade as either massive gravitons or massive scalars, those are not the ones which you're going to observe in a LIGO-like experiment.
Okay, I get it.
Yeah. Okay.
Thank you.
Thanks. Yeah, thanks for the question. Yes. So the only caveat in all of this is we have done it only for non-spinning black holes. And the reason is just because it was hard enough to do for non-spinning. So the next thing we are going to do is for spinning black holes. And then tidal dissipation, which is something I can talk about later, has also not been taken into account. But this is, again, a subleading effect, so it's not important. Okay, so before going further, let me give you a quick couple slide summary of how do you do this post-Newtonian stuff and why it makes sense. So if you look at the gravitational waveform, this is a cartoon of a waveform that I've done. So it roughly has 3 phases. You have the inspiral phase, which is this long phase where the two objects which are orbiting each other are going around in circles for a very, very long time. And then they get closer to each other, the frequency increases, the amplitude increases, they merge, where you have this big peak, and then you have this ring down phase, where you have this one deformed object, which is kind of wobbling around and settling down to its final form. So the inspiral phase can be attacked perturbatively, and you can do this using something called a post-Newtonian expansion, which I'll explain. And in this phase, you don't have to know the equation of motion of the object. So it's because the objects are still very far from each other, there is a world-line effective field theory description, which I'll also explain. So this phase is amenable to perturbative methods. In the merger ring down phase, so the merger phase is extremely dirty and it cannot be done analytically so far, although people are making progress using self-force techniques. So the merger phase has to be done using numerical relativity. So you don't really have much analytic control there. And in this phase, you can't really deal with objects as being point particles very far from each other. The full internal structure comes into play because these things are getting very close and hitting each other. And then in order to make sense of the whole waveform, people have constructed these phenomenological models called effective one-body models using Hamiltonian formulation in spiral merger, ring down, etc. So the phase I'll be focusing on today is this inspiral phase, which is this one, and I'll not be considering any of the merger ring down phases. All right, so let me give you a quick 3-slide summary of what is this post-Newtonian way of doing things. So this goes by the name of non-relativistic GR or post-Newtonian EFT. So the idea is the following. If you take a binary black hole system and you so if you consider such a system, if you're observing it, let's say with a LIGO light detector, what you're going to see is this is lambda gravitational wave, the wavelength of the things that are coming in. The problem naturally has the separation of scales, which is why you can do an EFT description of it. So there are 3 different regimes. One where you're standing very, very far away from it, and then you observe the gravitational waves that are coming in. Or you could be sitting very close to one of these objects, and this is what is called the internal zone, where you're only sensitive to the size of the object and things happening at that scale. And then you can have a near zone, where you are not close enough to a single object, but you're kind of sitting at the orbital separation scale, right? And now if you do some back of the envelope calculations, you will convince yourself that this orbital scale is essentially suppressed by, in comparison to the size of the object as 1 over v squared. So this is just the Virial theorem saying kinetic equals potential energy. And now if you go further and you try to see what is the wavelength of the emitted radiation in comparison to this orbital scale, you get a further 1 over v suppression. So you see already from here, you see that for small velocities, so this v is the orbital velocity of the binary. So for small v, lambda gravitational wave, the wavelength that you observe, the orbital scale of separation, and the internal size of the object, these are already hierarchically done. And this is essentially why you can do this effective field theory way of doing. This is something that people have been doing since the late 90s, and then this was reinvigorated in the early 2000s when Ira Rothstein and Walter Goldberger started doing this post-Newtonian EFT thing. Okay, so let me very briefly explain how one does this calculation, and then I'll give you the results. So in the near zone, which is where you are sensitive to the orbital size of the object, the theory that, so if you want to describe dynamics at this scale, then the theory is just so first let me describe everything in GR. So the theory is Einstein-Hilbert. You have to gauge fix it. And then you describe the motion of these objects as some point particles. So the gauge fixing that is usually used is the harmonic gauge. That is the canonical choice that is done for this problem. And then for the point particles, for the particles, you can write the action as a point particle action, which is just the particle moving on its world line. And then you can have some tidal effects. So in GR, in 4D GR, if you have black holes, then you don't have tidal terms. But if you had neutron stars, or if you go beyond GR, then these tidal terms are non-zero. And if you have two of these objects, then you need to have the mass of the object, world line of the object, and then the corresponding one for the next one. So this is the full action that describes the system that you're working with. And now at this orbital scale, when you are at small velocities, things are still very, very far from each other. You can expand everything around flat space. And then the perturbation that you write on top, which I call this h mu nu, and you do an expansion in it. And then you can arrange everything in terms of an expanded Lagrangian, and then you can compute the conservative part, which is the attractive force between these two objects. And then you can arrange this very neatly as Feynman diagrams. These dashed lines are just gravitons being exchanged. And then for practical purposes, when this is done, it is useful to do this, to decompose this h mu nu in terms of scalar, vector, and tensor, and this just makes life simple. So essentially, this is how you do computations in the near zone. And what it tells you is what is the potential between these objects. And so it's essentially, this will give you Newtonian potential and then corrections to it, which are being caused because of GR. Okay, so that's the near zone. And then in the far zone, when you are really sitting on Earth and trying to see what is happening here, because you're sitting so far, you don't really see the effective size of the, so you are at a scale which is very different from the orbital scale. And then at this scale, you can reasonably describe everything effectively as some source, which is given by this T mu nu. So T mu nu or TAB here describes the shape of the source, which is the blob describing the binary. And then you can do a multiple decomposition of this, exactly as you do classical mechanics. You just take mass moments, current moments, etc. And using that, you can then describe the effective shape of this blob, which is these two objects moving around. So if you have very low resolution, you can think of it like this, that the blob just looks like a blob. So that's like the mass of the object. If you can see a little bit better, then you see, oh, it's not actually one big blob, but it's a blob which is undulating because two objects are moving around. And then the next thing you would see is the quadrupole moment, which is the rough shape of this thing as a star. And then if you can see, if you can keep increasing the resolution and keep seeing things better, then you will start seeing higher and higher multiples. So the quadrupole moment is really what enters into the leading order calculation for the waveform, etc. So the waveform is very simply just time derivatives of the quadrupole moment. And then from there, what you can compute is how much energy is the system losing to gravitational wave radiation, which is the one you observe. And this energy is compensated by the binding energy, which is given between them. And then if you run through this calculation in some detail, you end up with the phase. So all I want you to take away from here is the two observables which you see on Earth are the waveform, the amplitude, etc., and then the phase of the waveform. And these are the two things that we are most sensitive to in order to see things if they are in GR or if they are out of GR. So combining what I told you on the previous two slides, so if you're given some kind of theory, so if you're given GR, and you wanted to find out what is the waveform, what is the phase, you would need to compute the binding energy in the near zone, and then do this calculation in the far zone, and then match them. And that's how you compute the waveform, for example. So before going to the full dictionary, let me show you two representative cases, one of which only involves higher curvature terms and another one which involves both the scalar and higher curvature, so that you have some idea of how the thing works, and then I'll just give you the full results. So the example I have chosen for higher curvature terms is cubic gravity. So this is the simplest non-trivial thing you can write down in 4 dimensions. Again, I'm working in an EFT sense where these coefficients here are supposed to be small. Right? So this is my full cubic gravity Lagrangian. As in, if I wanted to write down every possible combination of 3 Riemanns and every possibility of contracting it, these are the only 3 independent things I can write down. Everything else will have, so essentially I can rewrite every other combination using Bianchi identities as things which are proportional to the Ricci scalar, etc., and they're going to vanish in vacuum. So these are the 3 invariants that you can write down, and this is very well known in the literature since many, many years. In particular, these coefficients here, alpha, beta, and gamma, you see that now they carry mass dimensions because I have not put this m lambda outside, which I'll do in a second. Okay, so if you start with this and you say, okay, what is the first non-trivial correction that these R cube terms are bringing to my action? Then if you do an expansion, you will see that the first thing that you do is you get a 3-point graviton vertex. And then you say, okay, using this, if I compute what is the leading order correction that I get to GR, so you evaluate your integrals, etc., and then the result you get is this. So the cubic terms correct your potential as a 1 over R to the 6, right? And then you have the coefficient beta. So this is the term that gives you the leading contribution. Okay, now you put back your mass dimension. So like I said, this beta 3 is carrying dimensions of mass. So if you, again, this has 6, so this is 3 Riemann, 6 derivatives. And then the Ricci had 2, so you need to have 4 powers of L, this L to the 4 in order to balance things. And because, again, I'm working in gravitational units, so this L is G M over C. So this, you see, this is again M to the 4. This is the M lambda to the 4 that I had on the previous slide. Okay, so you do this, and now I'm writing things in terms of a dimensionless number, beta bar, and then all the dimensions are captured here within this G M lambda over C squared. So if I do this and I rewrite this expression, then what I get is this. So this 1 over R to the 6, I've written it as 1 over R, and then the rest of them like this. So this piece here, so again, mu is the reduced mass and m is the total mass. So mu times n is just m1 times m2. So this is just the Newtonian potential, G m1 m2 over R. And then you have this other piece which is correcting things. Now, if you look at how things scale with velocity, etc., and you use the variant theorem, you get Gm over R goes as v squared. And then long story short, once you have done all of this, you see that the correction to the potential at leading order goes as the Newtonian potential times something which scales as v squared over c squared to the 5. And then this m lambda, which is the scale of new physics here, divided by total mass to the power 4. So this v squared over c squared to the 5 is what is called the post-Newtonian parameter, as in how many extra powers of v squared over c squared do you need on top of the Newtonian result. Okay, so this is what I just showed you is the result from the potential. How the potential comes from this Lagrangian. However, like I indicated before, if you have objects beyond GR, if you have black holes in a theory beyond GR, you also have tidal effects, and just considering point particles is not enough. So then you also have to compute things using the tidal Lagrangian, and when you do that, you essentially get something very similar. You also get a 1 over R to the 6. You have these tidal coefficients. You put all the dimensions back, and at the end of the day, you get literally the same result. So the upshot of this is, if you start with this cubic theory and you just compute the conservative part, the potential, the force with which things are pulling each other, you see that these are corrected at a 5 PN order, and they scale with this new mass scale, which you have put in as m lambda over m to the 4. Okay, so this is the near zone calculation. Now you go to the far zone and you try to compute what happens to the radiation. So I will not run you through the calculation, but trust me that when you do all of this stuff, you get literally the same thing. You also get that the waveform and the phase, they both get corrected at 5 PN with exactly the same mass scaling. So what I've shown you here is one trivial, or the first non-trivial example of the problem that I posed a couple slides ago. So what I've now shown you is if P was equal to 3, then this A must be equal to 5 and B must be equal to 4. Sorry, is that a question?
Yeah, so I had a question here. So you're considering radiation coming out, but here you're not considering radiation damping. So
absolutely,
why is it so? Yeah, is it? What are the assumptions going here regarding neglecting those?
Right. So this radiation is this is just the on-shell graviton that I'm observing. If I consider radiation, so I can essentially consider self radiation. So so in the GR literature, this is what people call tail and memory effects. So essentially, if instead of considering that the binary is just moving around on a flat spacetime, if I consider that the binary itself is also denting spacetime, and the waves that it is emitting are getting essentially scattered back to the binary, that's the equivalent of taking these radiative effects into account. So in GR, these are subleading. So these start appearing at 4 post-Newtonian order in pure GR, where GR is getting corrected already at 1 p.m. If I did the same thing with higher derivative corrections, they're going to be subleading, which is why at leading order, they're not going to be important.
Okay, and because they, even though they're subleading, they lead to damping of several things, like in electromagnetism,
Absolutely.
we know that. So those are
Absolutely.
not observable in this case, or they don't contribute to any of this tidal deformability or anything like that?
So they will not contribute to the tidal deformability, but they will contribute to the inspiral tails, which is again subleading. So all I'm presenting here is the leading order correction that you're going to see. If you consider what happens if you consider subleading ones, then those effects become important.
Okay.
Yeah. So this is I'll show you in a couple of slides. This is exactly something that we want to do and we have started thinking about. So these tails and memory effects, and then tails of tails and tails of memory effects, as they're called. But yeah, so for this work, we haven't done it just because it was subleading. But next, we want to improve this and make it more and more accurate. So we are going to introduce those terms.
Okay, thank you.
Thanks. Okay, so let me quickly go to the second example, which is in the presence of a. Yes.
Can I, in the previous one, previous slide. So if I put back M Planck, which one of these would be M Planck? I mean, where would I?
So the M lambda. So maybe it's easier. So if you want to go between gravitational and high energy, maybe it's easier to see it here. So this L to the 4 is what is capturing the extra 4 space derivatives here, right?
Okay.
So in gravitational units, this L to the 4 becomes M to the 4. If you use high energy units, this L to the 4 would become 1 over M Planck to the 4.
Okay. And so when you write M over M lambda, then
yes,
or M lambda, so that would be in usual units M over M Planck, is it?
This would just get inverted. Yes, indeed.
And so this M, can you give me an example for what this scale M would be?
Yes, yes, I can. So let's say you want, so let's say you don't want to take this to be Planck scale, and you want to say, okay, observationally, what is the most I have constrained it, which is, let's say, kilometer scale.
No, one of them I would like it to be M Planck, and then some other scale to be some scale of physics, right? So it should look like some M over M Planck kind of suppression. Is that
so? I would say M Planck is I would say choosing M Planck is a very high energy biased way of doing it. I mean, you can do it for sure, but I would say if you just want to be really to the spirit of observations, I would say M lambda is the scale of new physics, and that is the scale at which. So the right question to ask is that to what scales have I actually verified GR, and so below which scale do I don't know if GR is true or not? And the observationally relevant answer for that is a kilometer. You can, of course, choose it to be a very, very small scale like M Planck. That's completely fine. But I would say, to be very honest, if you really want to test this with observation, you should put the scale of new physics to be a kilometer. And then this M here would be the scale of the objects which are merging. So in this case, there would be like, let's say 2 or 3 solar, or let's say 10 solar masses.
Sorry, do we have some example of a theory where M lambda is much larger than M Planck? But then the leading order still agrees with gravity. I should get Newton's constant fine, right? But it should be a small correction about that. So is there an example of such a theory?
So again, when people try to do these calculations, they take M lambda as a small parameter. So you can take it to be M Planck, and then you would get your. I mean, so if you start with any top-down theory, the usual new physics scale that you put in is M lambda. That's completely fine. You can do that. I'm just saying that you don't have to do that. You can also choose something which is much larger, and everything would still be consistent with the observation. So even if this was a kilometer, this is still consistent with the observation.
Yes, but do we have any example of a theory which will allow me to lower that scale?
I mean, if you just take cubic gravity, for example, with M lambda being a kilometer, this is completely consistent with the observations. It doesn't violate anything.
Okay, all right.
Yeah. However, if you really wanted something that comes from a top-down construction, then the most natural thing to say is, okay, yeah, because you don't want to introduce a new scale to the problem. You say, let me just take the most natural scale and construct out of my constants, and that turns out to be M Planck, which is why we take it. So, in principle, there is no problem with it.
Yeah, if we do that, then I guess the observables would be severely suppressed, I suppose, right? If I put it to M Planck.
Absolutely. Yes. Yeah.
Okay,
So, yes, so that's actually a good point. Okay, so if you just want to look at the scale of this term, the M lambda over M term, and let's say I take M lambda to be a kilometer first, and then we can take it Planck later. So to be observationally true to what we can measure, if you actually take this to be a kilometer, which is, I don't know, like a solar mass, for example, that's a kilometer. So and the M downstairs like 10 solar mass. That's the purview in which LIGO is measuring things. So this would be 1 over 10, so like 0.1, and this B here is 4. So you see, this is already 10 to the minus 4. This is already small, but not ridiculously small that you cannot hope to measure anything. Now, if you make this to be a Planck scale instead of kilometer scale, then you can see that this thing is just going to get very, very small.
Okay. All right. Okay. Yeah. Thank you.
Thanks. Okay.
Hey, Shubhendu, one more.
Yes. Yes. So, let me go back.
Yeah. If I think we don't need to go to the higher order, right? Because if we increase P, it will be even more suppressed, right?
Yes.
So that will never be testable.
Right. So the point is the following: if you increase P, indeed B is going to go higher. I'll show you a full dictionary in a couple of slides. But the point is the following: if you really believe that every term that should be there in the EFT is realized in nature, then it gives you a prediction. So like this will tell you that, okay, if this alpha bar 3 is non-zero and alpha bar 4, which would be the next term, is non-zero, and alpha bar 5. So if all of these are non-zero, then the prediction would be that, yes, the first thing that you would see would scale as M lambda over M to the 4, and that's it. However, if you are an experimentalist and you tell them this, that, okay, this is my prediction, they would say, okay, but what tells you that alpha bar 3 is not, is somehow accidentally not 0, right? So, I mean, as a theorist, I would say, well, unless I can show you there's a symmetry which is taking care of this, it's not 0. But okay, as an experimentalist, I don't care. I just want to know what is the most agnostic way of testing it. Let's say nature has somehow chosen alpha bar 3 and alpha bar 4 to be 0, and you've started with alpha bar 5. So you've started with P equals 5. So in order to be able to test things, because like I said, you need to have a match template where you have something that you can compare your data with. So in that spirit, you would want to know every possibility that whatever P you have or whatever derivatives you have, what is the corresponding things on the right-hand side. So in the spirit of this, you would want to know the full thing. But I completely agree that if you are using a naturalness argument, then you say, okay, all these coefficients are non-zero, then the leading order thing in a higher curvature theory would essentially start with 4, and that's it. Yes.
Okay. Thank you.
Thank you. Any more questions? Okay, then, sorry, was there a question?
Shubhendu, please continue.
Yes. Okay. Thank you. Okay, so let me quickly talk about the scalar example, and then I'll present the dictionary. So the other case that you can consider is you don't just have higher derivative terms, but you also have scalar degrees of freedom, which are coupled to higher derivatives. So the simplest thing you can write down is just a scalar with the canonical kinetic term coupled to the Gauss-Bonnet invariant, which is this G2 here. And now so I'll skip all the details and just give you the answer. So if you now compute the binding energy, both from this Lagrangian as well as the scalar tides. So when you have scalars, you have the usual tidal deformations of the black holes in this theory, but you also have scalar hair to these black holes, and these can also deform independently. So those are what I call scalar tides. And you can imagine, because the scalar is loosely bound as compared to the object itself, it's easier to pull the scalar apart than to pull the horizon, which is why they appear at a lower PN order, so which is 3 PN here in this case. For black hole, the tidal effects start at 5 PN if you just look at the horizon. All right, so if you take a scalar degree of freedom, this is the Einstein scalar Gauss-Bonnet, and you do this computation, the conservative sector gives you that you start with a 3 PN deviation. And then if you compute the gravitational waves, you will get the same thing. It also starts at 3 PN. However, when you have a scalar, you can get something much more interesting, which is that the observed degree of freedom. So in the previous case, the observed degree of freedom was the massless graviton, the spin 2 particle. But then if you have a scalar, the scalar can also go on shell, and you can also observe that. And this has major consequences, because the massless spin 2 graviton that you observe on shell only starts at quadrupolar order. It doesn't have dipole. That's just how GR works. But if you have a scalar, then you can have a dipole component as well, which is not present in GR. So this is a leading contribution as compared to GR, which is why people put a minus sign here just to say that it was not there in GR and you are doing something on top of GR. So if you have scalar radiation that goes on shell, you will actually see something significantly different from what you normally see in GR. And this is something which observations are most sensitive to, and this is what every experiment tests for the, whenever there's a new signal, this is the first thing that is tested. Even beyond gravitational wave observations like LIGO, Virgo, Kagra, when there are PTAs and these kind of experiments, this dipole radiation is also the first thing that is attacked, which you can see. Okay, so now I've shown you two examples of how these calculations are done in detail, and then you can do the integrals, etc. So let me skip ahead and just show you the final result of what the dictionary looks like. Before that, let me just say one thing. So the idea here was, if you have a space of EFTs, gravitational EFTs, which are all possible modifications to GR, how do you constrain the space of EFTs from the kind of observation you make to what kind of theory this comes from? So the usual way of dealing with the space of EFTs you don't consider all of these EFTs as physical. You can filter your set of EFTs by putting some kind of constraint. So you can put causality constraint. You can say I only want EFTs which give me second order equation of motion, etc. So you can do all of that. And usually once you do that, you have a smaller set of theories, which is the ones you consider. However, if you're doing this way of doing things, which we have showed you, this kind of bypasses this. So it gives you the same result, but because it's only picking the leading order term, it is not sensitive to all of these things. So it kind of makes life a little bit easier, that you can take the full space of EFTs and you can directly read off what is the mass dependence and the PN dependence of the result. Okay, so let me present the dictionary really quick. So I have categorized this into the possible space of EFT theories into four different kinds. So you have higher curvature, you have EFTs where you only have higher curvature corrections to GR. You can have higher curvature terms and also derivatives of the curvature. You can have higher curvatures plus scalars, and then you can have all of the above. So higher curvatures and their derivatives, scalars and their derivatives, everything coupled to each other. So the first category is what I was showing you before. So if you have Riemann p times, if you run through the calculations, what you'll find is the correction. So if you have this class of theories, corrections always start at 5 PN. And then the mass scale goes as 2p minus 2. So this is exactly what was being discussed a few minutes ago. So if this p was 3, this would have been a 4. But if p is higher, then this number goes higher. Okay, so now if you consider also derivatives of curvature and not just this, so you have Riemann to the p, but it's so instead of just having p of these, you can also have 2n derivatives of these and then p minus n. So the whole power of this is still p. In that case, when you compute things, you will see that the deviations start not at 5 PN, but it can be lower depending on what this n is. So if n was equal to 0, for example, so this would again go back to this case. But if n is 1, for example, then what you're essentially doing is you're stealing derivatives from Riemann and putting it inside. And this would mean that you would start seeing things at lower PN order. This is what I was trying to say before, that if observationally you start seeing things at 5 PN, then you're guaranteed that you don't have these kind of derivatives or scalars. But if you start seeing things lower than 5 PN, then the dictionary gets more involved and you have to read things case by case, and you can essentially figure out where things came from. Okay, if you had scalars, this is the example that I showed you before, but now generalized to p powers, then things start at 3 PN. The plus and cross are just the standard GR polarization modes, but you will also have longitudinal modes which come from the scalar dipole radiation, and those scale very differently. So those are leading compared to GR, and they have this. And then you can read up the mass scaling, which is a bit more complicated. And now finally, if you put everything together, then you can go on and essentially you can construct what things look like. So this is the full set of observationally relevant things that you can do on the right-hand side. And then depending on what you see, you can read things on the right-hand side and come back to the left-hand side. One thing to note here is there is a degeneracy between some of these things. So for example, this one could be degenerate with that one, etc. And then how you break the degeneracy is by either looking for these breathing modes, as they're called, the scalar radiation modes, or by looking at what power of P appears and so on. Okay, so very quickly, let me summarize what I've told you so far. So I've showed, what I've tried to impress upon you is that if you look at observations and you see something which goes higher than 5 PN, then you know that these come purely from higher curvature terms. And if they're lower than 5 PN, then they come from higher degrees of freedom or scalars, etc. And then using the mass scaling, you can narrow down what class of theories they come from. And then the question is, okay, this dictionary is okay for non-spinning objects as long as you're considering leading order. And then there were lots of questions already, which about things that you can do further. So the first thing that you can do is, or that should be done, is to consider spinning black holes instead of non-spinning black holes. And the reason is, once you introduce spin, these PN orders shift down to lower order. So instead of things starting at 5 PN, you may have things starting at 1.5 PN, because spin just makes things appear earlier in the post-Newtonian order. So this is something that I would like to do next. Then you have something called tidal dissipation, which essentially means that when you have your black holes circling each other and then radiating. So far, the calculation that I've shown you is how do you look at the radiation which is coming towards you. However, because the black holes are going around each other, they're also radiating towards each other. So I mean, a black hole is radiating in every possible way. So its partner can also absorb some of that radiation. And what this means is that the partner's mass and spin is also going to increase when this happens. If you take that into account, this is what people usually call tidal dissipation or tidal heating. This is something that typically shows up at 4 PN order instead of 5. So this in GR. So when you do things beyond GR, this will have some other effect. So one other thing which would be very interesting to extend this would be to consider tidal dissipation effects. So this is kind of fairly obvious how to do it. It just has to be done. Then there are these tails and memory effects, which we had a small discussion about before, which is how do you do radiation reaction on this? So if you have gravitons emitted by the system, so you have gravitational wave emitted by the binary, but then they get backscattered off the potential and then fall back into the binary, this is going to correct things. And what is the effect of this, both for the conservative part as well as for the radiative part? So this is what people call tails and memories, and then combinations of these things. And then lastly, what do you do with the ring down phase, which is the phase where, which is the last phase where everything has already coalesced and then things are ringing down into a stationary state. That state is also amenable to perturbative calculations. So this is an inspiral thing that I showed you, which has post-Newtonian. And the question is, can you do something similar in the ring down, which does not have a post-Newtonian part, but has amplitudes of quasi-normal modes, etc. So this is also something we're actively thinking about. Okay, so sorry, can I ask how much time do I have? Because I wanted to say a few more things.
You can take 20 more minutes.
Okay, perfect. Thank you so much. All right, so far, what I have showed you is what happens when you have a black hole in a theory which is GR or something which is beyond GR, right? So the assumption under the hood always was that I have black holes. However, you can loosen the assumption and say, what if it was not a black hole, but some other compact object? And this brings me to one of the other things that I think about a lot, which is compact objects. So this is something that I spoke about when I was there last time. So I will be very, very brief and just give you a little bit of introduction so that I can get to the kind of things that I would like to do further in this direction. So again, let me just give you a very quick reminder of why I care about this problem and why one should question, or why it makes sense to question the black hole paradigm. So black holes, as we have argued, are very good objects. They're very consistent with things that we've observed. And then the question is, why would you even consider an object which is not a black hole but something else? Okay, observationally, gravitational waves, which is what we have seen, and then electromagnetic data, which is experiments like the Event Horizon Telescope. So all of these are giving you things which are consistent with objects being black holes, as in you have compact and heavy objects, but they don't probe horizons, right? So you can say that things are very small maybe, but you don't really have ways to probe really if you have a horizon, which means that alternatives which look like black holes but are not black holes, are still viable alternatives. And there are error bars which are small, but it's not crazy to think about these objects. From a purely theoretical point of view, black holes have issues. So if you consider a curved black hole, for example, the exterior is smooth and regular, everything is good. But in the interior, you have closed time-like curves, you have singularities. There is no known smooth solution in the interior that connects to the exterior. You have Cauchy horizons, etc. And all of this has led people to question, is the curved black hole solution the real solution, or is there something that should smoothen it out? In this context, one of the things that people have wondered is, okay, if you have a resolution to the singularity, so if you remove the singularity, would the object still have a horizon? Or would the resolution of the singularity also get rid of the horizon? So this, again, people have thought about this for decades. This is still under active investigation. There is no resolution for it. But this makes you wonder that is it possible that you can have objects, or you can construct solutions which are horizon-less solutions, but which still somehow mimic black holes? And then phenomenologically, the question is, if you could construct such a solution, there are indeed examples where you can construct a horizon-less object that does mimic a black hole really, really well, with only subtle differences. So in this context, what people have tried to do is construct objects which are called black hole mimickers, which are essentially compact objects which look like black holes when you're far away, but then when you get close to it, they might be different. And here is my cartoon way of writing down a few of them. So depending on how large these objects are, so the size of the circle just tells you how big the object is in relation to its Schwarzschild radius. So you can have things which are as compact as a black hole, and you can have things that are much, much larger. And then you can have things in between. So a lot of this was already known, and people have been working on this since the last 25 years, roughly. So my contribution in this field has been to essentially construct a new class of solutions, which we call ADS black shells. And the reason for constructing something new is we wanted something which you could write down as a well-posed problem, and you could actually solve things to figure out what kind of properties these objects may or may not have, and how do you make progress in this field. So one of the big questions in this field is, can you construct an object, or is any of these objects dynamically stable to perturbations? And sadly, the answer turns out to be no for most of them, except boson stars. But then boson stars don't have surfaces. They are diffuse bosonic clouds. So they're a bit different from what we usually think of as black holes. So these ADS black shells are the first example of an object where dynamical stability has been shown nonlinearly. We have done this for radial perturbations, and now we are doing it for non-radial perturbations to extend it everywhere. And then there are other questions like, do these objects have stable light rings, which are essentially features in space-time where crazy things can happen. So what people have tried to do is construct objects which have stable light rings so that you can actually ask these nonlinear questions. But then it has not been possible to do it so far, again, apart from boson stars, but like there are different class of solutions. So again, for the ADS black shells, all I'm trying to say is these are the kind of motivations, which is why we constructed this object. So what we have done is over a series of works spanning the last few years, we have constructed these solutions from high energy results. We have tried to look at observational signatures of this. Very recently, we constructed rotating solutions, which is also a first in this class of things. And then I've spent a lot of time also exploring observable signatures of this, both in gravitational wave data as well as electromagnetic data. So all of this work is in collaboration with these four people. So this Ulf Danielsson is a professor in Uppsala University, Sweden. Giuseppe is a faculty in Rome. Luis Lenner is a faculty at Perimeter, and Franz Pretorius is a faculty at Princeton University. So let me very quickly just give you a one-slide summary of the main results so far. So in the context of I will omit the construction of these objects because I talked about it when I was there last time, and I don't want to go into it in detail. So let me just give you the observationally relevant things that have come out of this program. So again, this is the gravitational wave. This is the gravitational waveform that I showed you before from the merger of two compact objects. So again, you have the inspiral merger and the ring down phase. So the kind of things that you would hope to observe, which will differentiate a black hole from a non-black hole in the inspiral phase, are spin multiples. So if you have a compact object which has a horizon and it's non-rotating, then the metric outside is Schwarzschild. If you lose the horizon, the metric is still Schwarzschild because of Birkhoff's theorem. But now if you have something which is rotating and it has a horizon, then the metric outside is Kerr. But if you have a rotating object which does not have a horizon, then the metric does not have to be Kerr. And in general, it's going to be very different. And one of the challenges in constructing black hole mimicking objects is how do you figure out what the metric is outside? So one usual assumption that people do is they just assume that the metric is Kerr and then move on with it. This, in my opinion, is not a good assumption because if you don't have a horizon, there is no reason for the metric to be Kerr. And many solutions of Einstein equation are known, which are exact solutions. If you don't have a horizon, you can still write down exact solutions to Einstein's equation, which are rotating. So then the challenge always is, if you have a rotating compact object, what is the metric outside? So I tackled this question a couple of years ago and then constructed rotating solutions. And once you construct them, you see that they have multiple moments which are different from Kerr. In particular, for the objects that in question, if you look at the quadrupole moment is different from the Kerr quadrupole moment by about 1%. The next moment, the octopole, is of the order 10% different. The hexadecapole is of the order 30% different, and so on. So because these objects have slightly different multipolar structure from Kerr. What it means is that the inspiral waveform is going to reflect this. The phase is going to be slightly different, and this is something that can, in principle, be addressed. And these are, as you can see, very high PN effects. These kind of tests, which are checking the Kerr hypothesis, are being actively performed at LIGO, Virgo, Kagra when they're comparing with data. So these are things that you would reasonably expect to see, which will tell you what is going on in the universe. So here I have showed. I've included a picture of what the rotating black shell looks like. So essentially what happens is this is a fluid system. And when the object starts to rotate, the fluid is not a perfect fluid. And then you have this intricate pattern of matter and heat flow, etc., which gives you very, very interesting relativistic hydrodynamic things that you can then work with. Okay, so one other thing that you can that makes black hole mimickers different from black holes in the inspiral phase is that they have a tidal love number. So this just tells you how deformable is the surface of the object. So if you had a black hole, the surface is rigid, and if you try to pull on it, so if you put another object in another object orbiting it, the tidal force from that object will not be able to deform the horizon of a black hole in 4D. But if you don't have a black hole, but you have a black hole mimicker, then it is possible, because it has a surface and not a horizon, to deform it. And then we computed this tidal love number, which shows up at 5 p.m. So this turns out to be a small non-zero number. And then this will have a very, very minuscule effect in the phase of the inspiral. So these are potentially things which you can hope to observe if you have enough precision in your data. And then the other thing that we were able to construct is these quasi-normal modes, which tells you how does this black hole mimicker ring down once it has passed merger. And this is again so this is a summary of what it looks like. So this omega c, which is the orbital frequency in the light ring, and then this lambda, which is somehow telling you how things decay. So these are very, very close to Kerr, with a difference of about 0.5%. So again, these are different, but these are not significantly different that they would look very, very different from Kerr. So the point is, if you do these calculations, what you see is things are sufficiently different from Kerr that if you had very high resolution, you'd be able to see them. But they're still not so different that they would be inconsistent with what is observed today. And the interesting thing about this model that we've been working with is that it does not have any free parameters. You get what you get. So if you get this value for the observation, that's it. There is no way to change it to something different. So if observations tell you that things become inconsistent, then it's good, because then you can move on and do something else.
Shubin?
Yes.
Why do you consider ADS thing? Is there any specific reason to consider ADS type of background?
Right. Thanks for the question. So it's not so the background is not ADS. So the way these objects are constructed is that the interior of these shells. If you think of this object as the ADS black shell, the interior contains ADS space, and the outside is still Minkowski. So the way these are formed is by vacuum tunnelings. So essentially by doing a Coleman-de Lucia tunneling, going from Minkowski, which is metastable, by forming a vacuum bubble of ADS. So ADS is contained within this bubble, and you would not see it outside. And the reason we constructed such an object is because if you try to write down some fundamental theory where you can do this vacuum tunneling, so you can write down a potential which gives you both a metastable Minkowski and a more stable ADS, so that you can actually compute the instanton and do this transition. The theories that we were considering only allows for ADS or Minkowski solution and not a de Sitter solution. So it was just a natural thing to do this for ADS.
I have.
But again, the background.
Yeah, I have.
Sorry, go ahead.
Sorry, you complete what you were saying. Otherwise.
Yeah, so I was just trying to reiterate that the background is not ADS. So the background is Minkowski. This is non-supersymmetric 4D Minkowski universe that we live in. The ADS is just contained inside this bubble, and you wouldn't see it from outside. Yes.
So I had kind of two related questions.
Yes.
One is, you were just saying that there are no free parameters. So what kind of quality data do you need? How much improvement relatively in order to be able to see any of this stuff? That is one question. And the second question is, if you don't see anything at all, what is it that you're going to put bounds on? That's not clear to me. Yeah.
Yes. Thanks. Those are very, very good questions. So firstly, how much what precision do you need in your data? So there are two kinds of data. One is the gravitational wave data, which I showed you, and the other is electromagnetic data, which I wanted to talk about on the next slide. So for the gravitational wave data, you actually don't need a whole lot more precision. So with next generation detectors, so these things called Einstein telescope and cosmic explorer, I think people looking for tests of the Kerr hypothesis are already confident that you should be able to test spin multipoles to the order of 1%. If you can do that, testing spin multiples to the order of 1% is already enough to tell you if this thing is in or out, right? To test the tidal love number is much, much more tricky because this is a very, 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 very small number. So just to give you a context of what this means, if you had two neutron stars of the same size, this number would be about 1,000. So you see, it's like 10 to the 5 suppressed. So this I think is very, very hard to check. So the tidal love number is you should not think of this as observable, but the spin multiples are very, very much possible to test. And then for quasi-normal modes, if you take single events, so the loudest gravitational wave event we have so far is 2501. So the one we had earlier this year, which has a signal to noise ratio of 80. Even with that, if you just take a single event, quasi-normal modes, you cannot constrain to be less than 1% level. But then there are these methods of stacking where you take multiple events in the same mass range and you stack them together. If you do that, then it is possible to get sub percentage precision on this. So this is also something which is very, very testable. And then your second question is, if you don't see any of them, then the answer is very, very clear. At least for this one model, which is the only one that you can actually compute anything, you would definitively say that this model, this is not what happens in nature. Now the question is, if you see that, so let's say you see a different deviation. So let's say you see this delta, so the change in the mass quadrupole is somehow different from what you predict here, or you see a bigger change in the quasi-normal modes. This would essentially tell you that there is something else which is happening. So the black holes are not black holes. They are some other object which is not captured by this model. And then it's up to people to figure out what is that object and how do you go about constructing it. Does that answer your question?
Shubhendu, I just wanted to ask you if these objects that you constructed, two of them,
yes.
They merge together, then what will be the final object that is forming after the merger?
Right, very good question again. So we have been thinking about this for many months now. So there are, right, so the expectation is that these two objects will merge to form a new, bigger object. And the reason the expectation is the following. When we did accretion tests on this, so when we took one of these objects and then hit it with a large amount of mass and then tried to see what happens, what you get is that this object just becomes bigger and then acquires that mass. So you get a new, bigger object. So the expectation is that when you get two of these things hitting each other, you would transform into another object, which is the same thing, but much bigger. But now the question is, how does this happen? So the way each of these objects is formed is by quantum tunneling, is by doing this Coleman-Deluccia way of doing things. So if you have two of these things, then the question is, are these two, when these two things want to touch, are these going to tunnel into a new configuration which is bigger, or are they going to merge like soap bubbles? Essentially, you will have junction conditions where you have two surfaces intersecting and then you will pop up to a new one. This is something which we don't know which of these is going to happen, and this is something that needs to be investigated.
And when you discuss about tunneling, so
yes.
Usually in quantum field theory sense, tunneling is always disallowed because it goes proportional to exponential minus volume.
Absolutely.
So
yes.
when you have a larger area forming and larger volume forming, sorry, so then the tunneling probability will also reduce. So
absolutely.
is it possible to rule out some things of these, some mechanism?
Right. So it's not quite that simple. So if you just take one of these objects forming, if it was an empty shell with nothing on top, then the probability would indeed just be e to the minus s, like you mentioned, and it's suppressed. It's a macroscopic number. It's very, very small. However, this is not how this happens. So the formation of this is triggered by a collapsing shell of matter, which is carrying some entropy. So essentially, you have a phase space amplification. So you have your e to the minus s, which is the probability of this thing nucleating, that's this gamma. And then you have in front of it something which is proportional to the entropy that this object is going to carry. And the argument is that this number is large enough to compensate d to the minus s. So very similar arguments have recently been used for another class of objects called frozen stars, which also have some tunneling mechanism for forming. And then in the past, they have also been used for these constructions called fuzzballs. So I think this is an argument which people have made over and over, that the entropy of the collapsing matter is just going to give you more options of where you can tunnel, and this is just going to amplify your tunneling rate, and you're going to get order 1. But to my knowledge, this has never been rigorously done. So I cannot tell you definitively that this is what is going to happen, but the expectation is that you should, essentially just because you have many, many more degrees of freedom to tunnel into, you will get something which is macroscopically probable to form.
Okay, thanks.
Thanks, yeah. Okay, so okay, now I'm running extremely low on time, so I will spend 1 minute on this and then tell you about something else on the next slide, and then I'll finish. Okay, so the other observable which is relevant today, apart from gravitational wave, is also electromagnetic observation, because this is also something that you can do today and has possibility of distinguishing black holes from non-black holes. So here on the left-hand side is the GR-MHD simulation that I did for a black hole with moderate spin. So the kind of features you see here are a photon ring, which is the brightest part of the image, and then an inner shadow, which is the darkest part of the image. And then using these two, you should be able, or this gives you enough discerning power to distinguish between black holes and non-black holes. So on the right-hand side, I've again showed these for curved black holes. So the blue line is the same as the photon ring, and the white is the inner shadow here. And now if you do this computation for this ADS shell, so again, the reason I did for ADS shell is because that's the only concrete well-posed problem that we have come up with, or that anybody has come up with so far. If you have another model, you can do the same thing for that. What you see is, so these dashed lines are now the result for the black hole mimicker, and the solid lines are the result for the curved black hole. So you see that there is a small difference between them. In particular, the inner shadow is much bigger, which is a very, very sharp distinguishing feature and something that can be easily ruled out or ruled in. And then the other small difference is the shape of the photon ring. So this blue line here versus this red dashed line there. So these are very, very close. But then if you look at the appropriate quantity that are measured by detectors, then you see there is some difference. So these are the kind of distinguishing features which I think are important to construct for any object which people want to be a black hole mimicker. So again, the only reason I'm looking at this object is because I'm most familiar with this. This has some motivation of where it can form, and this gives you well-posed problem that you can actually answer. But in principle, this whole program can be done for any object that people care about, and should be done, I think, in this rigorous way, so that you can actually get some yes or no answers at the end of the day. Okay, so then there are lots of things that can be done here. So I will, in the interest of time, I will just mention maybe 2 or 3 things. So the first thing that needs to be done here is to understand tidal heating. So when such an object is in a binary, because it has a surface and not a horizon, it's going to get tidally deformed. It's going to heat up. The perfect fluid on top is going to do things, and that will have some effect. The full quasi-normal mode spectrum needs to be computed. So these are things that I would like to do. On the other side, you can do a full accretion GR-MHD study, which I think is extremely interesting for multiple reasons. So usually when you do these kind of calculations, so essentially what you're trying to do is how does magnetized plasma accrete onto this object, and what is the real thing that you see, not just computing these critical curves. So usually if you do it for black holes have purely ingoing boundary conditions at the horizon, which is what we are used to doing. But then if you have non-black holes, you can also have partially reflecting boundary conditions. And this is a slight challenge to do for MHD, because the force-free equations that you write down are not so easy to write down in the case where your boundary conditions have changed. So this is something that I've started investigating, but it's still a long, long way to go. So this is something that I would hope to do in the future. And then the other question is, okay, there are also jets that form at least around M87. We see this huge jet. The question is, do non-black holes also form jets? If so, how do they form it? How do you understand them, etc.? So this is also something which I think is super, super exciting. And then the other thing is, what are universal properties of these objects? And not just this one object in particular, but then the whole class of objects. How do they look like? What is a universal field that will tell me, is it a black hole, or is it one of these classes of objects? So these are the kind of things I would like to work on in the black hole mimicker camp. And then I would like to end with this other super, super interesting thing, which I have to mention. So I'm sorry, I'm going to take exactly 2 more minutes, and then I'm going to stop. So there is this very interesting problem of what is the moduli space of gravitational collapse in GR. And I've been thinking about this for a while now, and I think this is probably like one of the next nicest things that can be done in GR. So the problem is the following. Let's say you take some space, and you start with some matter configuration, and you let the matter configuration collapse. The question is, how strong does the matter configuration have to be to collapse into a black hole versus disperse out to flat Minkowski space? So this question has been asked several times in the past. In particular, you may be familiar with Chopwick's result from the early 90s. So what he found is that if you tune the strength of the initial conditions of the collapsing matter field, so if you have something which is not very strong, then you will not form a black hole, but you will just come down to Minkowski. Instead, if you have something which is very strong, you are going to form a black hole. And then there's a critical value of how strong the initial conditions are, where you're barely forming a black hole, and that forms a critical naked singularity. And then he found this nice scaling behavior. Since then, people have tried to understand this boundary between black hole formation and non-black hole formation. So there is this famous result by Christodoulou from 1994, which was which essentially showed that the weak cosmic censorship is not true and you need strong cosmic censorship, where he started with smooth data and then he found that you can form naked singularities out of them. So then these are, you can form naked singularities, but then they lie within the black hole region. People have also constructed critical stars, which are, again, critical solutions, but they're not singularities, and they don't have horizons, so they're star-like solution. Very recently, Ryan Unger and Christoph Keller, they constructed non-critical extremal black hole solutions, which are essentially violations of the third law of black hole thermodynamics, and they showed that you can do this. And then again, much more recently, they've tried to do this with other systems, which are called Einstein-Vlasov systems, where you can form these solutions and they turn out to be critical. So all of this is to say that this boundary between black holes and non-black holes is a very interesting, is still completely unexplored. It's not clear what happens to these boundaries, what happens when you go to these edges. And there are many things here which can be done. In particular, there are 3 concrete directions which I have started to think about and would like to work on in the next few years. So one of them is what happens if you have axisymmetric systems. So most of these are for spherically symmetric systems because axisymmetry is very hard to deal with. So there is a result from 1994 showing critical collapse in axisymmetry, but this has never been reproduced since. And the reason is because of gate choices. So recently people have started looking at it, but it's not clear if you can, if these results are correct or how do you actually go about it. So this is something that is extremely interesting to see. You can actually formulate the problem in 5D gravity, which reduces to a 4D system. So I can go into details, but I don't want to, which has the promise of actually giving you some very nice results. So this is something that I would like to look at. And the third thing is looking at extremal disks in the context of violation of the third law of black hole thermodynamics. Right. So there are these kind of questions which I'm also interested in. I will skip gravitational wave lensing and just end with this last message that we have entered this era of gravitational wave astrophysics, astronomy, however you want to call it, where we have a window into this strong regime of gravity where curvatures are large and we can actually make meaningful observations. Data is going to be here soon, which is going to tell us everything that we need to know. The question is, can we be smart with our theory and actually try to, be ready with predictions of what we expect to observe? Because once you see something, you can always post it. I think the challenge to understanding fundamental physics is, can you predict things, given that these observations are just around the corner and they're going to be here in the next 15 to 20 years. So with that, I would like to thank you.
Okay.
And sorry again for really going over time.
No problem. Thank you, Shivendu. If you have any more questions.
Hi, Shivendu Manjari here. So
yes. Hi.
Yeah, in your first part, so I was thinking that you already can get result up to 3 PN, right? So I was thinking because see, for double pulsar, not the Hull stellar, for double pulsar, the orbital dynamics have been tested up to 2 PN. So now if in future we discover a black hole neutron star binary, so in the orbital dynamics like periaston precision or that decay of orbital period, those are now measured with 2 PN, right? And with black hole neutron star might be 3 or 5 PN orders are needed. So because here, as far as I understand, you are planning only black hole. But if you want to include spin, will not it be better to give do the orbital dynamics, including spin, because if you have black hole neutron star, you might neglect the spin of the neutron star, right? It is almost like a test particle. So do you think it will be observable in 10 years from now or something?
Yeah, I mean okay, so this is a good angle to think about it. If you right, so if you're thinking of isolated events, so right, so the spirit of this dictionary is actually not isolated events, but essentially by stacking multiple events, because in order to read off the mass scaling, you need to have more than one event so that you can read off how it scales. So just for the PN order, single event is enough. But yes, I think this is a very good way of thinking about it. So if you're thinking about single events, I think what you mentioned is the right way to go. Right. So also in the context of things happening in the next 10 years, I would say it also depends on the mass of the things you're considering, right? I mean, if you're considering intermediate mass ratios, for example, then these planned DESI-GO and other experiments, so I mean, these decihertz detectors that people are also planning in India, etc. These also might play a role. If you're thinking of like comparable masses, then I would say probably 10 years is not enough, because you would still need at least some 3G detector to be turned on to see these kind of things. But then maybe with things like SKA, which you are more of an expert on than I am, maybe it's possible to say something in the next decade. I don't know.
Yeah, thanks for the fascinating.
Yeah.
Any more
Thank
questions? Anyone in the online? So if you have no more questions, let's thank Suventu again. Thank you, Suventu.
Thank you so much.
Keep.
Should I disconnect or?
Please saying that they all enjoyed the talk.
Oh, thank you. Thank you so much. Thank you. Very nice to see so
Okay,
many
thank you.
friendly faces again. Thanks.
Bye-bye.
Bye-bye.